I don't have enough authority.
Come?
Non sono abbastanza autoritario.
Sì, sì.
Allora, we get back to Luca's classes. He has to run right after. So if you have a very urgent question, you can raise your hand and ask during the talk. So floor is yours. Don't waste time.
Thanks, Roberto. So welcome back, episode 2, episode 3 back to back. The fact that I have to go because I have a plane is my problem, okay? Don't worry about that. When you worry about getting the most out of this. So I left you yesterday as magnet engineers, right? So you know how to design a magnet, how to build a magnet, more or less. So what I want you, is this off? Ah, yeah, maybe a good idea. All right, so what we'll have a look in episode 2 is essentially how did we get to find and understand what superconductors are, and what did we do with them for high energy physics. So as I said yesterday was a climb. Okay, we got up to the institute, and from now on it's more of a descent. It's a bit more relaxed. You're going back to Florence. And then I'll talk to you a bit about other uses of superconductivity. It's also useful so that you know what else can you do with superconducting magnets in particular. Because as you will see in episode 3, that's something which I think is very valuable as one of the results of our community, high energy physics. All right, so introduction to superconductivity, discoveries and principle. I'm sure you may know all of this, but the equivalent of the frontier physics at the end of the 1800s was actually to understand material properties at very low temperature. That's when people managed to actually understand the thermodynamics. They managed actually to get fridges to run, and excellent physicists debating about what would happen to materials if you went to very low temperatures. So in particular, what happened to resistivity. So people started to understand, electricity, electrical currents are moving particles, and if the particles get cold, what happens then at low temperature? And there were different theories, like the resistance would get lower and lower as the crystal moved less and less, and the particles were more and more free to move. So essentially a resistivity curve that would go like this, like the blue one. Another theorist that says, no, these free particles will actually freeze as you get colder, and then you will get the red curve. So resistivity would actually increase. Now beware that one of the proponents of this red curve was actually also Lord Kelvin, okay, Professor Thomson. And so even excellent physicists, as you know by now, they can go wrong, okay? Among others, Lord Kelvin said X-rays are an hoax, that he had the smallest molecule of faith in aerial navigation other than ballooning, and the famous quote, there is nothing to be discovered, everything needs to be measured better, right? Okay, it was at the verge of quantum physics. Okay, fine. Now, something was happening at the same time, and it was the attempt to actually get it lower and lower temperatures just because of this, find material properties at low temperatures. Now, it so happened that at that time, the best way to keep fluids cold was using dewars, and dewars were made of glass. So it was bottles of glass inside glass, complex tubing. And so what you needed, if you were a successful physicist, was excellent glass blowers. And that's what Kamerlingh Onnes had, the Dutch scientist, who actually used the perfection way of doing cryoplants at that time. So these were excellent glass blowers and technicians to get liquid helium for the first time. And in fact, at that time, he was the only one who could get liquid helium. And helium gets liquid at 4.2 K. And as an anecdote, he was showing liquid helium around, even to the Royal Society. So just imagine this physicist Camerling honest, dressed like that, with a dewar of liquid helium, boarding a plane and going to the Royal Society to show what happens if you liquefy helium, right? That's amazing, okay? That was physics at the time. Now, having access to 4.2 K, he could measure low temperature material properties. And he wanted to resolve the question, do the particles freeze or do the particles move freely? And that's the curve he measured. Actually, he did not measure it himself. He had a postdoc doing that. And the postdoc was measuring the curves, and then suddenly he saw nothing. So the reaction of Kamerlingh was, well, go back and measure again. So he was measured again and again. And always at 4.2 K, there was this drop. And eventually he entered in his journal that thus the mercury at 4.2, this was mercury, by the way, mercury wires, mercury because it could be purified very much. It would be a pure metal as would be required for the experiment. So at 4.2 K, mercury entered a new state, which owing to the particular electrical properties, no resistance, was called the state of superconductivity. Okay, that's 1911. So this is the discovery. Now, what does it, how do we explain that? So it took many years. In fact, it was 50 years later that Bardeen, Cooper, and Schrieffer actually understood the mechanisms by which you can understand how these particles, once the material is cold enough, they can actually flow into the material at zero resistivity. Now, in a normal conductor, this is a cartoon just to explain it, okay? So it's not necessarily proper physics, but so in a normal conductor, what happens is that the electrons going through the material actually scattered by the defects of the crystal, and the scattering appears as work, and the work appears as a resistance. Okay, so that's what explains the resistance to the flow of an electron in a lattice. These are obviously only the conduction electrons. They have relatively large energies, few electron volts, and they're at the boundary of the Fermi surface. Okay, just to put things in proper perspective. And the defects, they may be faults in the crystal. They may be thermal agitation. Okay, so the atoms, they actually displace from the perfect positions that they are supposed to have. Because in a perfect lattice, actually, the electrons would see no resistance. They're a free gas. Now, in a superconductor, though, what happens is that the electron is not alone. Electrons are bound by what you can imagine like an elastic. Like there's a force between the two. And this binding mechanism is such that if an electron gets scattered, the other gets anti-scattered. So they maintain the momentum between the two. So these paired electrons, they move and compensate each the scattering of the other. They go straight through the lattice as if they were not scattered. Actually, what happens is that these paired electrons in the vicinity of the Fermi surface, they pair, they have opposite momentum and spin, and they end up as bosons. They actually condensate in a lower energy state, such that that lower energy state is free to move through the lattice. Okay? So this free movement appears as zero resistance. And it appears if there's not enough energy to break the pairing. That's a very important concept. So there's a gap between unpaired and paired, and this gap makes that if you're in the pair state, condensated, then you not have resistance. If you break it, then you do have resistance. Okay, so what is the mechanism? So what is that magic elastic that couples the two electrons? So just imagine again in the lattice, one of the two electrons paired, moving, and that is moving and it's actually causing an attraction, right? Positive ions, negative electrons, the lattice is actually vibrating as the electron goes through. But that means that there's a positive charge in the wake of the electron that has passed, and that positive charge acts as an attraction to the following electron. It's like when you go cross-country skiing. I don't know whether you have that experience. If you follow the tracks of somebody in front of you, it's easier, okay? Somebody has already made the tracks. Somehow there's a force on the tracks that binds the two. Now, lattice vibrations are nothing else but sound. That's phonons that propagate through the lattice at the passage of the charged particles. So what couples the two electrons is actually phonons, okay? So, and as you can imagine, the force exerted by phonons is not much, which means that that energy gap is not very wide. There's a little energy between the condensed state and the unbound state. And so that means that it only works if there's very little thermal excitation in the lattice. So it only works at low temperature. That's why you need to cool it down, cool the material so that the thermal agitation does not break the packs. Okay, so that's what Bardeen, Cooper, and Schiffer formulated in 1957, and they actually got the Nobel Prize for that. Okay, so obviously it's simple enough, but I think it was great insight in that. Now, it only works at low temperature, okay? But we don't know which materials. And actually, if you look through the periodic table of elements, there's a lot of materials that are superconductors if you cool them enough, okay? Nearly half of them are superconductors, even more. So Bernd Matthias, also a material scientist interested in superconductivity, was trying to prove that you can get superconductors beyond the BCS theory. Essentially tried to disprove BCS. He wasn't convinced that there was all this that was behind that. And what the BCS tells you is that there's a theoretical limit around 30K. Okay, so that's the braking mechanism of the best effective coupling. So he was looking at many superconducting compounds, elements, but not only. And the legend goes that he had drawers where he had actually elements. They would draw out, combine them, make a new element, and then test it. Okay, so he was actually doing a periodic table physical. Okay. Now, unluckily, he died in 1980 because in 1986, Berners and Müller at the IBM labs in Zurich, they actually found out that there are materials that become superconducting above 30K. Okay, so that was the big discovery. Okay, and from there on, there was a big excitement until materials came up like YBCO, so yttrium barium copper oxide, that is superconducting up to about 100K. So obviously, it's not BCS. And by the way, it's not really clear what's the superconducting mechanism for these materials. Okay, so it's not just BCS. Now, they're very serious here at the discovery photograph. And they're much happier when they got the Nobel Prize. So it's a much better picture of them, right? Okay, even in Zurich, okay. People can get happy. Right, so, so that spurred a new interest in material research in superconductivity. And this is a timeline of critical temperature, okay? If you remember, we were talking yesterday about this critical surface, critical property, critical temperature is the first one, beyond, below which you're superconducting, now you understand why. Is the first property that people were looking for. Now, what we have are materials like low temperature superconductors. Now you understand why, below 30K. That's why they're called LTS, niobium-13, niobium-titanium. There's many, but those are the two that we'll come back to. They're technical superconductors. HTS, high temperature superconductors. Now you understand why, above liquid nitrogen, above 77K. So in particular, YBCO, so yttrium barium copper oxide, and BISCO. Bismuth, strontium, calcium, copper oxide. Okay, these two here. There's more materials, in particular one that was discovered in the year 2001, magnesium diboride. People were puzzled because that material is actually a strange low temperature superconductor. It's a dual band. There's various modes in the crystal that make that you can couple at temperature of about 40K above the 30K of the BCS. There's the iron-based superconductors. I believe you may have heard that. That's a big hype, especially for our Chinese scientists in applied superconductivity. There's a claim that this material can be cheap. So we'll come back to cost later on. But they have very high, relatively high critical temperature and relatively high critical field, okay, so that you can generate fields with them. And finally, there's a high temperature, room temperature superconductors. There's quite some research in material science to find out what is the limit of superconductivity. And so there's materials here that under very high pressure, hundreds of gigapascals, they get superconducting, hydrides and similar compounds. The only problem is that they are only superconducting at the pressure equivalent of the center of Jupiter, okay? So the room temperature superconductors over there, not with us. All right, so we saw TC. There's actually a much more fundamental definition of a superconductor, and it's the fact that contrary to classic material, where if you have a material, you change the field, and the eddy currents in a conducting material, they would tend to expel the field. So if you raise the field in a normal material, you get eddy currents, and the field profile is actually pushed out. In superconductors, if you cool them down with a field, they also expel the field, okay? Their lower energy state is the one where they see no field. And this was a discovery of Meissner and Oxenfeld in 1933. So complete field exclusion shows that what we see in superconductivity is a phase change. Okay, that's an important concept. Okay, it's a different phase with respect to normal conductivity. And that's how the BCS actually, that's the hint they brought to TCS. And this effect is what you see when you see these pictures of levitated magnet on a superconducting pellet. Okay, the superconductor doesn't want the field, tries to expel it, which means it exerts a force, and the force is pushing the magnet away. Okay, and that happens when you just cool it down. Okay, you don't need to move the magnet. The magnet lifts up, and it's a very nice experience to do if you can do that. Now, these superconductors, to expel the field, they have to do work. And remember, 10 Tesla is equal to 400 bar. We did it yesterday. So it's a lot of work if you want to expel the fields that we are interested into. So if you had to do it with what is called a type 1 superconductor, pure materials, the material will actually not be able to do that. It would crush under its own magnetic pressure. But there's other ways. So instead of pure metals, which have a critical field, okay, so the maximum field that they can expel of the order of millitesla or tens up to 100 millitesla for niobium. By the way, that's why niobium enters in cavities. So there's a different way that was found by Landau, Ginzburg, and Abrikosov, explained by them rather, found by Shubnikov in Kharkiv, a way that allows the field to enter into the material and organize itself so into small zones which are normal conducting, regularly arranged in a bigger zone which is superconducting. And that's a much more energy efficient way to let the field out of the superconductor, because these are normal zones, but manage a much larger field. So these type 2 superconductors, they have critical field of the order of 10 to 100 Tesla. That's much more interesting for us, okay? So if you look now into the two properties we talked about, so we talked about critical temperature, now we talk about critical field. The two are related. If you increase the temperature, you decrease the field you can tolerate. If you increase the field, you decrease the temperature you can tolerate. So essentially, in a BC-TC, critical field, critical temperature plane, what you get is that you get curve that explain that boundary we saw yesterday for the critical current surface. So critical field for niobium titanium, MgB2, niobium 13 of the order of 10 to 20, 30 Tesla. Critical temperatures of the order of 10 to 20, 40 K for MgB2, okay? HTS, and in fact, high temperature superconductors, they're interesting because they are 77 K, they're down there, okay, under K, but they're also interesting because they have very high critical field, they're up there, 100, 200 Tesla, okay? So they're out of the slide, I didn't plot them, okay? But they're very interesting because of that. Now, what about the current? Actually, you know from yesterday, you need current to generate a magnetic field. You don't need critical temperature, you don't need critical field. So, if you have a current flowing in that material, type 1 and type 2, the thing that happens is that the current generates a field, and the field and the current generate a force, and the force makes the current move, okay? So if that movement, which is actually a motion of what we call fluxoids, so the quantized amount of field that gets into the superconductor in the normal zones, if that movement is not kept, so it's not blocked, you generate energy. That energy increases the temperature. That increase in temperature makes that you lose superconductivity. Okay, so there's one more thing we need to do. So we need to lock the current lines, we need to lock the fluxoids, these quantum of flux that are penetrating into the superconductor, and we do that using what we call pinning centers. These are defects. Remember, when you concentrate the field, it's in normal zone. These defects are the normal zones inside the superconductor where you lock the flux lines. And you do that because these pinning centers, they exert a pinning force. Okay, depending on the defect, depending on the material, you have a certain force. What are these pinning centers? So I've taken two examples. One is niobium titanium, the other is niobium-3 tin, which are well known and understood. And in niobium titanium, which is an intermetallic alloy, you treat the material through various heat treatment and drawing steps so that you have precipitates. The precipitates are the white lines that you see here. They're alpha titanium in the alloy. And if you do the thing properly, you can make it precipitate with a spacing that is comparable to the spacing of the fluxoids at a certain field and temperature. So that means they're ideally arranged so they're blocking those fluxoids. So that would be the spacing at 5 Tesla 4.2 K. And that's where you get a peak of the pinning force. Okay? The same thing you can do with the niobium-3 tin, but there the defects are the boundaries between the grains. Niobium-3 tin is an intermetallic, it's reacted, it forms grains as it reacts, and between the grains, there's normal zones. So each of these grains has a boundary, and the boundary is the pinning center. Now, it doesn't take much to go from pinning force to critical current, because you remember the previous expression, so J cross B is a force, J is the current density, B is the field, F is the pinning force. Once you know the pinning force in a certain field, you can get the critical current, the current that can flow, equal to the pinning force. So the critical surface we talked about yesterday is nothing else but the ratio of the pinning force to the magnetic field. And that depends, obviously, on field and temperature. Okay? So, and that's how we get these surfaces that you saw yesterday. This is an example for niobium titanium, where we had a slice yesterday at 4.2 K. Typically, the values here at 5 Tesla 4.2 K is about 3,000 amp per square millimeter. That's what we have today as one of the standards. All right, so now there's various ways that you can classify superconductors. Type 1, type 2, you've seen that already. Conventional, explained by BCS. Unconventional, not explained by BCS. Okay, that's very easy. Low temperature superconductor, high temperature superconductors, or material classes. You may find them classified by elements, alloys, compounds, ceramics, pnictides, organics, sulfides, and so on and so forth. But the important thing is that there's a few of them that are actually technical. You can buy. Okay, that's what's important about them. So I mentioned niobium titanium. I mentioned niobium-3 tin. There used to be niobium-3 aluminum. That's actually a developmental material. You don't buy it. Magnesium diboride you can obtain. YBCO, BISCO, IBS. Okay, this is the year of discovery, and these are typical properties in terms of TC and BC. And I've already said that, but what's important is that for us, HTS are very interesting because of the high temperature, critical temperature, but especially because of the high field. So we can generate fields in excess of 20 Tesla, and for solid in excess of 40 Tesla. How do you make them? So niobium titanium is actually made by starting with a copper can. You put in that bars, which have a copper sheet, and then you put niobium titanium alloy inside. You put them in an hexagonal shapes, you arrange them, and then you do extrusion and cold drawing. And you go and heat treat, extrude, and heat treat, cold draw, and heat treat, and so on. Until you get wires like this, which is about 1 millimeter in diameter, with many, many filaments inside, of the order of a few microns, 6 to 10 microns for the LHC. A wire like this carries 1 kiloamp at 5 Tesla 4.2 K. Okay, that's kind of the reference point for niobium titanium. Niobium-3 tin, the other LTS, which is widespread, this is brittle. So if you make niobium-3 tin and then you try to wind it, it will break. I think there was a remark yesterday from Hitoshi. So indeed, it's very brittle, and you can easily break the niobium-3 tin filaments. So what is usually done is that by a different process, you actually put precursors one next to each other, bronze and niobium, or a tin source and niobium, and then you wind, and that precursors are drawn down like niobium titanium. Then you wind your magnet, wires or cables, and once they're wound, you cook them so that you have the intermetallic reactions. You bring them up to 650, 700 degrees C, niobium-13 forms, and from that point on, you're not touching it anymore. Okay, so you have to pot it to be able to mechanically handle it. A wire like the high lumi wire, high luminosity LHC, carries a current of the order of 1.5 kiloamp, that's also about a millimeter, at 12 Tesla, 4.2 K. Okay, so that wire is actually twice better than niobium titanium, both in currents, in field, and temperature. That's why niobium-13 is interesting. Bismuth compounds, they're made a bit like niobium-13, but, and they're also brittle, but instead of cooking them at 600 to 700 degrees C, you need to cook them at 900 C in an oxygen atmosphere. Okay, so that becomes a bit tricky. If you think about engineering ovens of the size of a magnet, 15-meter long, going up to 900 C, plus minus 1, okay, tolerance, and in an oxygen atmosphere, you realize that you have your safety on your back, and you won't be able to operate that furnace very easily. Okay, so that's a bit of a complex material. But a wire like this, which is also about a millimeter, carries a kiloamp, so it's always the same order of magnitude, but at this time at 20 Tesla, 4.2 K, okay, higher field. Finally, REPCO, or YBCO, europium BCO, gadolinium BCO, that's rare earth barium copper oxide. They don't come as round wires. The reason is that they're made by a physical process that deposits the elements, and it deposits them onto a substrate, and the substrate needs to be very clean and polished, because then you need buffer layers. As in the case of REPCO, the crystals, they need to be oriented so the current can go through. So it means that the buffers, they need to be textured so that the position of the elements of the YBCO, REPCO in general, is such that the grain growth happens oriented. Now, imagine growing essentially, you need a kilometer of these tapes or wires. It's a kilometer single crystal, okay? So it's not easy. It's a complex process. It's a rather expensive process, but once you master it, you can actually go for it. Now, same as BISCO as you see before, so about a kiloamp in a tape at 20 Tesla and 4.2 K. Okay, so what did we do with these things? And the story starts long ago in the 60s, where people realized, okay, we can make magnetic fields out of, in particular, niobium titanium, niobium zirconium. So niobium zirconium was a variant of alloys. Actually started off in 1954 with niobium. Okay, niobium cold drawn became a type 2 material because it was dirty. And a scientist in Tema made the first magnet that was used for detectors, actually. And then eventually in the 60s, things picked up with the discovery of niobium titanium and niobium-13, until Kunstler patented in 1960 a superconducting magnet configuration. It was clear already at that time that one needs JC, critical current density. You want a compact winding, and that's how many of these wires underwent material science optimization, so that the various materials, some of them died out, not interested, like molybdenum rhenium wires. It was substituted by niobium-13 and eventually niobium titanium that was discovered in 1962. So the orders of magnitude on JC at that time was about 500 to 1,000 amp per square millimeter at relevant fields, so a few Tesla and 4.2 K. Now, there was in 1961, very interesting, at high field magnet conference, and there was kind of a race between the various research groups. There was one by Kunstler, who achieved, from Bell Labs, who achieved 68 kilogauss, the 6.8 Tesla, barely surpassing the 60 kilogauss made with niobium zirconium solenoids. So he was using niobium-13 at that time. And then there's a story that's very interesting. So the Kunstler had a report to write for the Bell Labs, for his boss, Tannenbaum. And because he was working on magnets, he wouldn't write the report. And so Tannenbaum was complaining about that. But Kunze said, but I'm producing higher and higher fields, and that's very interesting. So they had what they call a Scotch bet. So Tannenbaum would pay a bottle of Scotch for every 3 kilogauss above 25 kilogauss. Okay, so 0.3 Tesla above 2.5 Tesla. And the first 10 Tesla solenoid was built a couple of years later after 2 crates of Scotch. Okay, and then they stopped, and he had to write a report. All right, so at that time, the magnets were affected by a phenomenon that is called flux jump. It was one of the perturbations that we talked about yesterday. The flux that is trapped in the superconducting material would collapse, generate energy, and make the magnet quench. So people found a way to deal with that phenomenon of flux jumps, stabilizing the magnets. Okay, so that's what we talked about yesterday. And the first uses were in the 60s for detector magnets. Now, it was also clear that if you wanted big magnets, you needed cables. And how to make cables, we were talking about 65, wasn't clear. Various configurations were looked at, and eventually 2 configurations stand out as the most promising one. One is to twist the cables and squash it. That's what is called now the Rutherford cable. Or the other one was to braid the cable and squash it. Okay, that's the braid that was developed at Brookhaven National Lab. Now, that's interesting because at Brookhaven, before that, in the meantime, the CERN ISR was being built. It's the first particle-to-particle collider. And that hosted the first accelerator superconducting quadrupole magnet. Okay, so that was the first use ever. And that was built, so this is a quadruple coil using single wires. Okay, so you can recognize the single wires here in the winding, and that's the IR of the ISR, where you have here the quadruples. Now, what was happening in the meantime at Brookhaven, where I said before there was the development of that cable, was that there was an accelerator in conceptual design, Isabel, eventually some R&D on magnets, and eventually groundbreaking in 1978 with a configuration that was foreseeing 2 magnets one on top of the other. The problem of that was that the cable braided that was devised and developed by Brookhaven was actually moving a lot. They had a lot of internal movements. Now remember what we said yesterday, perturbation spectrum, mechanics. So those movements were actually making the magnet quench. And the magnets had a hard time to reach performance. So problem as well was that the construction started before completing the R&D. So raising the energy to 400 GeV, which was a demand from physics, field from 4 to 5 Tesla, the construction started before the completing of the supporting R&D. And the result was that not achieving the performance and problems of cost, the project got canceled in 1983 after spending $200 million for the tunnel. Okay, so the Isabel tunnel was essentially already built, but the magnets were not ready. In parallel to that, a certain Robert Wilson at Fermilab, at that time he was a National Accelerator Laboratory, promised an energy doubler. He was very bold. He said that it would cost much less using superconducting magnets than using normal conducting magnets. And he said he would do that without exceeding congressional authorization of $250 million. Okay, that was what he had as budget given by the Congress. Okay, he didn't have magnets, but he promised that. So, and that's how the whole story started. So trying to put magnets in the main ring tunnel, starting off with the superconducting strands made of niobium titanium, various magnet configurations, and then eventually ending with a configuration that had a coil made of cables, Rutherford, inside a cryostat, inside a warm iron yoke. Now, the way they got there, also very interesting, was using what they called the Edison. They built dozens and dozens of magnets and eventually got it right. Okay, so it was possible at that time, but it was very interesting because I think some of that should apply also to what we're doing today. And so that's how the Tevatron was born. Okay, so machine started operating in 1983, was stopped when the AHC came up, got nearly to the Tevatron, so it was a 980 Tevatron actually, but never mind, and operated at 4.2K. That was followed by Hera, the Hadron Electron Ringanlage, conceived in the 70s up to the 80s, and then built essentially with the same concept of the Tevatron magnets. So you recognize here the coil, but the iron yoke was cold inside a cryostat. Okay, there was a change. There was more compact, and what was especially looked at was the effect of field quality. Okay, there was a lot of concern about field quality in superconducting magnets. There was a lot of work to understand them, as well as reference magnets. So there were two reference magnets for the two families of magnets that were built. We were feeding data to the controller circuits. So HERA started operation in 1991, closed in 2007, reached also about a Tevatron, a tera electron volt in the proton ring. And what you see here is the electron ring underneath. So above is the superconducting machine. Following these two, there was obvious interest in what is the next step. So in one of the next steps that was proposed in the US was the SSC, the superconducting super collider. So started off in 1983 with a heap up recommendation and ended up in 91 after founding a laboratory in Texas with a construction start, in particular the tunnel again. Various magnet configurations we're looking at, from low field, 3 Tesla, up to high field, 6.5 Tesla. And there was a question among the questions, why not to go to very low field and aim for high fields? Make the tunnel bigger. Yes, but once you have the technology for 6.5, that's what you use, because the magnet will not cost much less than the 3 Tesla, okay? So that led to the tunnel. Most of the tunnel was built, led to a lot of R&D work on magnets. And in fact, one of the difficult magnets was the booster magnets, not so much the collider ones. They had to be ramped so that they would have to bring the energy of the beam up to the point where you can inject into the main ring. That made that the cost that was initially estimated at short of $5 billion in 1993 ended up climbing up to $12 billion. So of course, the Congress got very critical about that. And in 1993, the Congress canceled the SSC after about $2 billion were spent mostly in the tunnel. Now, though, the result of that R&D was that the niobium titanium wires and the magnet technology improved a lot. There was a lot of additional understanding, and that led to a proposal that came from Brookhaven for a relativistic heavy ion collider, the RIC machine, and that had to be cheap. And in fact, the way to make it cheap was make single layer coils, this structural component made of plastic, and rely on the cold iron to retain the forces. There was a very interesting concept for dipoles, for quadrupoles, as well as the correctors. So that was successful because having these magnets allowed the RIC to be built in the existing tunnel of Isabel. Okay, so there was a very efficient reuse of the work that was done before. Finally, in parallel to the SSC adventure, there was in Europe the LHC. The LHC started off as well in 1984 with a conceptual study. 1994, there was a project approval by the CERN Council. I joined CERN in 1995, by the way. And eventually in 2008, we started commissioning the machine. Now, if you look back into 1984, ideas were very fuzzy for various configuration, PP bar, PP, one channel, two channel, one on top of the other, one next to each other. But a year later, after having selected the PP, the magnet design was strikingly similar to what we actually have in the machine today. So there was, Giorgio Brianti was a real genius working with his team in devising this magnet, which is the LHC dipole. Went through several generations of various models and long industrial realizations. The dipoles are not the only magnets. So what you see here is the zoo. So you have the dipoles here, quadrupoles, as well as lots of correctors, IRs, matching sections, and so on and so forth. That is the LHC. Started in 2008, blew up a few weeks after starting, got repaired in 2009, and is doing now physics at nearly 7 TeV. Well, that's high energy physics, but not only. I think it's interesting also to see what do we do with these wires and cables and materials. One thing is magnetic resonance imaging, MRIs. That's what the doctor sees, that's what the patient sees, but that's what the magnet engineer sees. So MRIs work thanks to a big solenoid that produces a horizontal field on the patient, very homogeneous in the zone where you want the resonance to take place, and then you use antennas and gradients to generate a point of field, and you sync into that frequency so that you can essentially slice the patient with magnetic field points, voxels, and then you reconstruct the amount of water, as an example, that is corresponding to a certain position in the patient. So these are these images that get generated today. It's a powerful diagnostic. It's not the only powerful instrument that is made with superconducting magnets. The other is NMR machines, nuclear magnetic resonance. That's how you understand the structure of proteins, you understand materials. And essentially, that's also big solenoids where you put a sample in there, and then you measure a resonance spectrum at various frequency, and the lines of resonance depend on the element or the combinations of molecules. And what happens is that if you increase the field, like it's done here, from about 5 Tesla to 20 Tesla, what you clearly see is that the spectrum actually gets much sharper. So you can understand much better which element is there and what the structure is. And in fact, if you look into the evolution of these machines, the NMR machines, you see that as a function of the year, the field has been increasing steadily up to today's realization, like this 1.2 gigahertz machine, which is not the top of the line. There's more, but is made with HTS, high temperature superconductors. Motors and generators, you can do with high field magnets, motors and generators with higher power density or higher torque density. Very useful if you build wind generators. Okay, so you know that the load at the top of the nacelle is important for the structure. And if you can make the structure, so the tower higher, you can make the blades longer, you can generate more power. So superconductivity gives access to that. There were demonstrators, going from normal conducting to superconducting. They were showing that indeed you gain that and it works. There's people who are looking into powertrains for planes, all electric planes. So they're actually based on a superconducting motor, a superconducting cable between the power, the fuel cell that uses liquid hydrogen, and then powers the engine, so the motor of the plane. I'm not sure I want to board the plane with liquid hydrogen and superconducting motors, but never mind that. Energy storage, okay, so I think I would skip that. Transformer, fault current limiters, magnetic separation, fusion, okay? That's a big use of superconductivity. And so the biggest machine which is being built in the south of France is ITER, the International Thermonuclear Experimental Reactor, where I singled out here toroidal field coils, poloidal field coils, a central solenoid. All of these are 10, 11, 12, 13 Tesla class superconducting magnets. And this machine, by the way, so it's about 25 meters tall and it's about 30 meters in diameter. So it's a massive, gigantic experiment. And of course, back to high energy physics, the detector magnets that we used in the past and we're using today are based on superconductor. Now, the usefulness is that you will need a lot of ampere turns to generate high fields, or modest to high fields, as you use in detectors. Usage of superconductors started already with the bubble chambers, argon. The big European bubble chamber, in particular, was the record magnet for stored energy for tens of years until the ITER center solenoid came up. Omega is another detector that was built at CERN, and that's what we have today, right? CMS and Atlas, you've seen these pictures. They're based on superconducting solenoids, this thing here, or a superconducting toroid, as you see in Atlas. And finally, a couple of one slide about other uses of superconductivity, which I found fun. So you remember the story of exclusion of field, levitation. So a few years ago, there was at the conferences, there was a machine that was brought around that was able to levitate this platform here. So you don't see the details, but this platform here is essentially the same as you see here. A magnet on a superconducting pellet. And that was able to levitate a sumo wrestler, So Naomi, 202 kilos. Okay, that was quite impressive. Okay, there's some things like that where at conference in applied superconductivity, you can actually stand on it and spin. Okay, so it's quite fun. So at that time, 1997 in particular, there was a letter of Professor Main, who worked in applied superconductivity at the University of Nottingham on materials. Now that letter was interesting because it came from the Church of the Latin Snakes, founded 1905, revived 1950. Okay, already by the letterhead, you get a bit itchy. They said they have a big interest in the machine. And they wanted to know how big is the magnet and can it be concealed beneath a floor? But especially, does it make much noise? And does it hurt? Because it will be me doing the levitating. Ooh. And the idea would be to pull back the curtain in the snake chamber and start to rise up from the ground. But if you send out that machine, don't send it to the natural law party. They are the very bonkers. And finally, I put in 5 pounds for you. This is only the start. Okay, and with that, I think we can end episode 2 for a short break and questions. So I guess, just to introduce the question, I think that answers what happens in case of a quench, right? Because there was a question, what happens to these super electrons, right? I believe you understand it now. I don't know where the question was coming from. Yeah. Know where the switch is. Right.
Thank you for the talk, and I wanted to ask if you know the theory, if what is the actual state of the art of the theory on thermal superconductors?
Room temperature
Room temperature, sorry.
Room temperature superconductors. So what I know is that people have achieved room temperature, so they have showed that there's superconductivity at room temperature. So I'm not a material scientist, okay? So I think you better do a proper scholar research. But people have gotten up to 273 K, so room temperature, or 300 K. And as I said, these materials, they are superconducting if they are under enormous pressures. So you need to put them under hundreds of gigapascals. So there's diamond anvils that are used to do that. So you put the material under pressure, and then you measure a magnetic moment, typically, because they are diamagnetic. So you detect the superconductivity through that, or you measure the resistance, with microprobes. These are, very small material pieces. They're not very useful from that point of view. So what people are trying to do is to induce pressures by modifying the crystal structure. So they take out some of the atoms, they put in other atoms that will deform the crystal, and then induces pressure inside the crystal. So there's work in this direction. But as we were discussing with Roberto before, one of the issues is that, remember the fluxions? They need to be pinned. And if you change the field and the temperature, the fluxions distance changes. Now, the other thing that changes is one thing that is called the coherence length in the superconductor. So that's the length upon which the field dies out inside the superconductor. Now, the coherence length goes from hundreds of nanometers at low temperature to tens of few nanometers for high temperature to sub-nanometers at room temperature. It's so small that you cannot pin the current. And from that point of view, if that is the physics, unless you find some other phenomenon, if that is the physics, those conductors, they will not carry current. So, ideally, yes, room temperature, they're not very useful if they keep extrapolating from what we know, unless somebody finds something else. And keep in mind, liquid nitrogen, everybody has it nowadays. So cryogenics is not an issue at that level. So very interesting physics, bottom line, but I'm not sure that it will be applied very soon. Maybe there's a question there. In the meantime, maybe I go ahead and I just wanted to show one thing. Yeah. There was a question, I'll come back to you. There was a question about the ends. So what happens in the ends? Because yesterday was showing just cuts, right? So the cuts are a line here. If this is an LHC dipole with two magnets, positive and negative, protons in opposite direction, that's the ends. That's when you curve the cable, and obviously you have to go outside of the plane because otherwise you have no space for the beam. So that's the end of what we call a cosinus theta magnet. And the way it's done is by winding with these machines, these ends, okay? I hope you can see that, right? I believe these answers. Sorry.
No problem. So now I have a second question after you showed that. So with the Rebco, hypothetically, will it be the same coil like or braiding as you have for like the niobium tin, or will there be a different, like, what do you think the manufacturing process will look like? How thick, how many layers of Rebco do you think we'll need? You know, that's my, yeah.
Right. Okay. With Repco, you can wind the same. It's a single tape. You can do cosinus theta. You can do blocks. You can actually do blocks, and blocks are, if you wind like a racetrack, and then you actually lift it at the end so that you make space for the beam. The problem with Repco is that these are cables. Okay, so it's not a single wire, and you put 30 of them, you make a 15 kilo amp cable. With Repco, you have a tape, and it's a kilo amp tape. If you want a 30 kilo amp cable, you should in principle be twisting the tape, but you can't. So the problem today with Repco is how do you make cables? Or how do you make magnets without having cables? I'll touch on that later on.
Then my other question, I mean, you're kind of alluding to this, but so is the overall design of the lattice more analytical based, or is it more theoretical based, or is it just like an interplay between the two? Because you showed all those nice diagrams with the various magnetic fields. So yeah.
Whether the
In
magnet
practice.
design is analytical based.
Yeah, just like the overall like layout of where the cables are. Is it more, I mean, you have the overall like theory, but then in practice, is it more analytical
Yeah,
or is it more theoretical?
Okay, so typically what happens is that you start off with a cross section, and then you feed that into a field program. You feed it into ANSYS or COMSOL. You feed it into custom programs, and then you get the results. And then you try and make sure that the stresses are okay, the protection is okay, and so on and so forth. I tell you, unless you understood what you're doing, there's no point in doing the numerical simulations. Okay, so you better understand the analytic before, because stresses can be wrong and protection can be wrong. So, okay, right. Should we go to episode 3? You feel like that? Okay.